Hi everyone, my name is Austin Nguyen, and I'll be presenting my topic on integrating algebra in applications for computer science. So here's a little preview of what we will be talking about in this presentation. We'll start with a review and then move into coordinate systems and then another review and then moving on to matrix transformations. So to start off, let's review matrices. It's important to have a strong understanding of the basics of 3D graphical design. And in order to do that, we start by understanding 3 by 3 matrices. So 3 by 3 matrices we know are to demonstrate a three-dimensional space. We're used to seeing the x, y, and z coordinates or the x, y, and z components. In computer graphics, we translate this to using unit vectors. And we do that by using the vectors I, j, and k rather than x, y, and z. And this is also generally seen in physics. So here we have a bunch of 3 by 3 matrices and their respective properties. We know we can add matrices together of same dimensions, and we can multiply matrices by a scalar. And then matrix by matrix multiplication can also occur depending on their dimension. So moving on, now we will discuss vectors. As everyone should know by now, vectors, uh, there are two vocabulary words that we should add to your vector understanding. There's a row major vector and a column major vector. A row major vector is just another way of saying it's a 1 by n vector. N in this case being 3 if you look at the image on the left. And then a column major vector would be an n by 1 vector, which in this case is a 3 by 1 vector on the image on the right. And three of either left major or right major vectors create one vector space, or one 3 by 3 matrix. And that is if they are linearly independent, because by definition of vector space, they must be linearly independent. And then remember, at its simplest, linear independence is found if there are no free variables, or if there are no vectors that are a multiple of another. And moving on, now that we covered vectors, let's discuss vector spaces. And we're going to be looking at them in our typical Euclidean coordinate system, or as we also know it as our Cartesian coordinate system. So by definition found in our textbook, a vector space is a non-empty set of objects, also called vectors, defined by addition and multiplication by scalars properties, and they are subject to 10 axioms or rules. And we should already know what those rules are, and if you forget, you can just refer to your textbook. I like to think of a vector space as a group of vectors that fit within a broader field, like a field of real numbers. The vectors that make up a vector space contain commutative, distributive, and associative properties. Two linearly independent vectors create a 2D vector space, and three linearly independent vectors, as I mentioned in the slide before, or two slides before, create a 3D vector space, as seen on the images on the top right. And if you look at the image on the bottom right, it illustrates a single vector labeled P in a vector space of real numbers of R superscript 3, meaning that the vector belongs to a field of all real numbers. And essentially, there exists a field that may contain multiple different vector spaces, and in each vector space, there exists subspaces, which we are discussing now. And by definition found in our textbook, once again, a subspace is a subset labeled H of vector space labeled V with three specific properties. These properties are, they contain the zero vector, there is closure under vector addition, and there is closure under vector multiplication by a scalar, as we learned in our lectures. It is important to note that vectors, vector spaces, and vector subspaces are all relative. They all depend on the coordinate system being used. And speaking of coordinate system, that is our next topic. So we covered everything so far with vectors, vector spaces, and subspaces. So now we need to apply that to computer graphical design. A crucial topic is coordinate systems because, as I said, everything's relative to whatever unit of measurement we are using. So let's start by introducing homogeneous coordinates. Extending the concept of a Euclidean coordinate system, 3D spaces are often represented by 4D vectors. And there are generally 4 components in a 4D vector. This is our I, our J, our K, and our W component, and that is the new one. The W component typically has either a value of 1 or 0 in its bottom or in its last index, depending on whether you look at the vector as a row major or column major vector. When W equals 0, the homogeneous coordinate represents a 3D vector. And remember, homogeneous coordinate is that entire row major or column major vector. And then when W equals 1, the homogeneous coordinate represents a 3D point. So the difference between here is 0 is vector, 1 is point. Moving on to graphical spaces, which is another topic within coordinate systems. And we use them to represent objects in a gaming environment or a virtual environment. That is, how do we use a coordinate system to visualize them? A vector space, as I said before, is a generalized abstract term. It is all relative. Applying the concept of a vector space, we can define a more definitive space within a video game. So the first new space we will discuss is called a world space. Just like a vector space, a world space is a type of vector space. As mentioned before, it is just a broader version. It encapsulates many other vector spaces though. So, as I said, spaces are pretty relative. In a gaming environment, every object has its own relative position in the world space. As you can see in the image here, there are 3 teapots. Each teapot is an object in itself, and it all lies within one world space. Now, if we dig a little bit deeper within that world space, we move on to the model space. And a model space can be thought of a vector space within that world space. There are a lot of spaces, I know. Each model space is representative of one object. In this case, each teapot is its own model space. During my research, I found it useful to think about vector spaces in another applicable context. And I like to think about it in astronomical context. Try to think about it as our universe as the world space. And then within that world space, there is a galaxy. And that galaxy is our model space. And in that, we have our solar system, which we can define as a subspace. And each planet within that solar system is a vector in that vector subspace. So it goes from world space to model space to subspace and then vector. Now that we introduce these new spaces, we know how objects are placed in a virtual environment. But how do we manipulate them, which is pretty important in games? We start by reviewing linear transformations. So a change in object placement is done through matrix transformations. Let's start by reviewing those transformations. So just a general definition as defined in our textbook. A transformation or function or mapping defined as t from r superscript n to r superscript m is a rule that assigns to each vector labeled x in r superscript n a vector t of x in r superscript m. So basically, a function defined as t will map the original x onto a new codomain or create an image, and that will be labeled t of x. So r superscript n is the domain of t, and r superscript m is a codomain of t. We can also call that as the image. Now, how does the math behind a matrix transformation work? This is still review. In a matrix transformation, matrix multiplication takes place. Transforming a vector x requires the multiplication by a unique matrix, labeled A, and we call this the transformation matrix, where the matrix A is called the standard matrix for linear transformation T, and E sub n is a respective column of the identity matrix. So now let's talk about rotations. As we learned in a two-dimensional space, the 2D rotation, the matrix for a 2D rotation is as found in the image on the top left, where that unique matrix A is equal to cosine phi, negative sine phi, and then sine phi and cosine phi. And phi represents the angle at which the rotation is occurring from a counterclockwise manner. Each column is represented by a vector which points to a position on the 2D coordinate plane, as we can see on the image on the top right. So this is basically just using a unit vector and just understanding how cosine and sine works to align our vectors accordingly. Now let's talk about it in a 3D sense. Remember, in a 3D context, we tend to use 4D vectors. We tend to use homogeneous coordinate system. So the difference here is the inclusion of that W component. Recall that when W equals 1, the homogeneous coordinate represents a point. And notice how all these transformation matrices have a W component value of 1. The presence of this 1 is crucial to maintaining that position of the object in the vector space. We don't want to switch it back and forth. We want to keep the object as a whole, essentially. And then just if we go back one slide, just look at the differences between the 3D unique transformation matrices and the 2D. If it goes back. Yep. That difference really is just the addition of the W component and the maintaining the 1 in the respective rows and columns, just so that we can maintain that shape and orientation. So next, let's discuss translations, which is another form of matrix transformation. Translation relocates the entire shape without disorientation and disfiguration. The translational matrix for a 2D transformation can be seen on the bottom left, which is the 3x3 one. And the translational matrix for a 3D transformation can be seen in the top right. The only change here really is the delta value, which is moving the whole object x, y, and or z. So there are other transformations that we've discussed in our class. There are reflections over axes, a point or an origin. There are contraptions or expansions, and there are shear transformations. Remember, shear transformations is basically just creating a diagonally shifted image. Now let's apply the concept of projections in a computer graphic sense. And projections is another form of transformation. Every object is placed in a world space, as we discussed before. Remember, the world space is the universe, basically. And in a world space for a video game, we must now choose a view space as well as a camera space. This is essentially the point of view of the user. So developers have founded a method called the lookat method to establish two spaces. The first space being the camera space, which is its position, and then the second space is the view space, which is how what the camera is seeing. The camera has a vector space, as I said, called the camera space. And that camera space determines the orientation of the camera to look at a second vector space called the view space. It's all a lot of spaces, but just remember, there's a camera space and a view space. And there tends to be two planes to consider within a view space. Remember, view space is what the area that we're looking at, not the camera's position itself. We're looking at what the camera is looking at now. There is a near plane, which is represented by this red line in the image here, and anything between the camera and the near plane is not going to show up in the game. This explains why sometimes objects disappear when they come too close to a video game character. I'm not sure if many of you play video games, but that's what happens. The same thing can be said about the far plane, which is much more intuitive, I'd assume, because anything farther than that far plane will not render within a computer game. But if you look at this image, there's something that you should also notice. We're talking about a 3D game, but this is in a 2D coordinate system. So how does that work? So how our next discussion is, how does this projection get made in a 2D coordinate system when it's being used for a 3D application? The answer is using an orthographic matrix. This is another transformation matrix. There are 4 parameters as seen in the image, which is the width of the view space, the height of the view space, and the shortest distance between the near and far planes. This is the definition of an orthographic transformation matrix in the video game sense. The orthographic transformation matrix is used to determine the range of view in a game. Now, but in order to determine the angle from the angle or field of view, which is basically from left to right, how far left and how far right we can see, there's another matrix that we can use. So remember, orthographic matrix is used to determine like how close and how far we can see, and then we need another matrix to determine how far left and right we will see. And that matrix is called a perspective matrix. Ignore the title on this slide here. That is a little error. So it is called a perspective matrix. This matrix is used to determine how far left and right a user can see from that camera space. So the difference in parameters between this matrix and the orthographic matrix is that the perspective matrix uses a scalar for the x and y direction, and that takes into consideration a variable named field of or FOV, standing for field of view. And FOV is just an angle. It's just an angle of how far in that forward from the camera space we can see. And that is basically a really simple version of algebra in computer graphics. So, what is the purpose of algebra in computer graphics? We can now answer this critical question. Notice how I didn't explicitly state linear algebra throughout this whole presentation, despite the fact that this project is for a linear algebra seminar class. This presentation actually delved into the complexities of a more advanced topic, or advanced concept called geometric algebra. Part of what was discussed today was linear algebra, and that was the review portion, but the new stuff we covered in a three-dimensional application just barely touched the surface of a geometric algebra. So at its essence, geometric algebra allows developers to extend into the third dimension and create a more immersive experience for its users, which pretty much makes sense, considering that we're talking about 3D games. And so that is it for my presentation. I hope you enjoyed. Sources can be found in the speaker notes of the slideshow, and then it will also be posted in the final slide of the slideshow. So thank you for following along, and thank you for listening.